now, I think.
Yep.
So
It's recording now. Yep.
Yeah, that's great. So thank you for joining us, and Greg, you can talk about your presentations. So we have plenty of time today, I think, but I don't know how long you plan to talk. We booked for an hour and a half, but just talk whenever, as long as you want to about your project.
Well, it's only been going for 4 weeks, so I don't think I'll have an hour and a half to talk about. But okay, ready?
Yeah, sure.
Okay, so I'm going to talk about using Piatics in machine learning, and why this is actually vaguely useful for computational linguistics problems. And then from there, I'll demonstrate an example of where this kind of technique absolutely slaughters everything else that's out there, which it worked far better than I was expecting. So the idea of distance crops up all over the place in machine learning. So for example, like let's say you're trying to draw a line of best fit through a data set. Then what are you aiming to do there? Usually you're minimizing something like the square of the distances to the residuals. Or there's another algorithm, the nearest neighbors algorithm, and you're finding the points in the training data set that are the shortest distance away from the test, or should have said test element. And DB scan, let's cluster points based on the distance. I mean, this idea of distance crops up absolutely everywhere. And axiomatically, what does that look like? Well, obviously, if we're having a concept of distance, so how far away are we from having the correct answer, then we need some kind of concept of a zero distance. So we need to have something like the distance metric of element A minus element A, some sort of difference there should be a zero. We'd also like to see that there's some kind of derivative. Now, you don't have to have that for all machine learning applications. You can have things that are not quite derivatives, like sometimes you see that where during neural networks, the function, the loss function is not necessarily have a derivative everywhere, but it's really handy to have the concept of a derivative of some kind, so that you can do things like gradient descent. I'd like to zoom closer to what the correct answer would be. And then there's a kind of a fundamental thing when we're talking about distance, which is the idea of the triangle inequality. If I have one vector and then another vector, so in other words, 2 points or a point and a distance change or something like that, then what I'd really like to see is that the distance from A plus, the length of A plus B should be less than or equal to the distance of A plus the distance of B. And so what that sort of sane geometry gives you is the idea that, okay, maybe I'm nearly at the correct answer. If I make a small change, I can't suddenly find myself miles away from the correct answer. That is, if I change my X and say my input X vectors, I don't want to suddenly appear somewhere completely different. So those really, when you look at any of the underlying mathematics behind any of the machine learning algorithms we tend to do, those are really the three things that you need in order to make these things work. I now talk about Kurt Hensel, who I actually thought this was a mathematician by the name of Weierstrass, but when I looked up on Wikipedia and actually did some proper research, Kurt Hensel was just a little bit earlier in defining exactly what he was talking about. So flicking backwards to the previous slide, we need zeros, we need derivatives, and we need the triangle inequality. And so Kurt Hensel had this very, very twisted, evil distance metric. It goes like this. Instead of working over floating point numbers here, we're working over integers. So the distance of the zero integer, the number 0, that's 0. Okay, that's good. That means we automatically get our 0 axiom. Then we look at x, and so first we've picked a prime number. Maybe your favorite prime number is 2, or maybe your favorite prime number is 3. So let's say your favorite prime number is 3. Then we look at the x and ask, is x divisible by 3? And if it is, then the P-adic distance is whatever your x was divided by 3, calculate the distance of that, and divide the resulting thing by 3. And if it's not divisible by your favorite prime number, then the distance of that x is 1. And you can also turn that into fractions, because like if you see that the denominator has a p in it, or the denominator is divisible by 3, then you just multiply it by 3 as many times as you need in order to get it up to being like no longer with a 3 in the denominator. And with a bit of staring at that, you'll realize that we've got the triangle inequality. And in fact, really scary, we actually have derivatives that two numbers are really close together if they're highly divisible by p, but you can actually do a well-defined derivative on that. And even things that you'd expect to happen, like the derivative of x squared should be 2x, that still works. Now, just as a reminder, we're only talking integers and fractions. We don't talk about floating point numbers because. So let me give away the ending of where I'm going to go on with this. The first is these Piatic metrics, when you apply them to machine learning algorithms, you end up with something that's ridiculously robust to certain kinds of noise. So if the problem that you have is noise that's got sort of some randomness that's going to modify your measurements, we'll do terribly. So if you're counting something and every now and then you might miscount by +1 or -1, that's bad. This is not going to help with that. If your randomness is when there's like background radiation, your measurements are higher or lower, not going to cope with that, well with that. But if the kind of noise you have is there's an underlying signal that's absolutely crisp clear, but then there's a whole bunch of random points that are of no relevance to the problem at hand, Piatics will pull that out. And what I think is the case is that a lot of linguistics problems and language problems fall into that space where most of the time words are spelt correctly and you can do most of your analysis on the correct words. And even if there's a lot of other words, it's not like the words could be one bit off. The word is either as it is or it's not. You might get some random spelling mistakes, but the underlying signal will be there. So that's the motivation on the Piatic metrics, is that we've got robustness to a certain kind of noise that crops up in natural language processing problems very regularly. Then it's also very, very challenging to come up with high performance algorithms because we've spent decades optimizing for floating point. And this is now talking about divisibility by p, and all sorts of things go very badly wrong because there's assumptions that we make that don't apply Piatically. It also gives this rather nice hyperbolic space that I think will also be helpful for natural language processing. I've got a long discussion as to why I think that's going to be really fruitful. But word to vec using real numbers, I'm predicting is going to not be as useful as word to Piatic fraction. So I've got to defend that, but not in this seminar. I'm just going to have to put together some results to prove that one as well. What else is interesting? You get this sort of halfway between a regression and a classification problem effect. So normally classification problems, I'm trying to predict some discrete value, like true or false. And then with regression problems, I'm trying to predict some continuous value. Well, if I'm working two-adically, then I'm really talking about zeros and ones because I'm caring about modulo 2, but at the same time, I've got continuity. So when I do these machine learning algorithms, I find that the regression and classification algorithms are almost sort of merging together, and they behave strangely, strange combinations of both. And what we also find is that because the Piatic algorithms are ultrametric metrics, we end up with these incredibly weird degenerate versions of the Euclidean algorithms. It seems like a whole bunch of things that should be different, like the K-medioids algorithm should be somehow different to hierarchical clustering. What I've seen so far is they aren't. They just sort of devolve into doing exactly the same thing. So there's a huge number of research topics here, and 4 weeks in, all I've managed to like completely knock over is just one linear regression. And so I'm desperately hoping I can encourage absolutely everybody to get enthused and start doing the same things and flesh out all the other Piatic sort of algorithms here. So moving along, if my mouse is going to let me. So a few little bits to make sense out of this. So if you've got P equals 3, then the numbers 1 and 4 are very close together because they're divisible by 3. Just popping back a reminder, we're looking to see if divisibility by your prime is what counts as being close. So 1 and 10, they're very, very close together because not only is it like 1/3 apart, they're actually 1/9 apart, incredibly close. And 2 and 29, they're just so unbelievably close together, you can barely tell them apart. As opposed to 1 and 2, they're far apart, and 1 and 3, they're really far apart. And you want to know a really small number? Yep.
Question just confused a bit. So 4 is not divisible. It's not divisible by 3, right? P is correct. 3, right? So maybe I just.
So 4 is quite a large. Yeah, 4 is quite a large number. 1's quite a large number, but they're very close together.
I mean, the formula says x divided by p if p divides x and 1 otherwise.
Diego, the x is the difference between those two numbers.
Oh, right.
Yeah.
Right. Yes. Yeah. Sorry about that. Yeah.
Yes. So yeah, we've got both the difference between things, like the distance apart, and then we've also we could look at what's the distance from the origin to some point. So for example, 3 to the 14 is very, very close to the origin. So it's a very, very small number. Two-adically, things become startlingly simple. So let's say I was looking at, tell me how far apart 93 and 21 are. So here's 93 written out in binary here, and here's 21 written out in binary. Well, when I subtract those two in binary, I'm going to end up with some number that has some zeros on the end. And really all I need to do is count the number of zeros on the end, and that's going to tell me the two-adic distance. And if I was doing a subtraction, then I don't even need to actually do the subtraction. I just start at the right and count the number of bits that are in common, starting at the right working leftwards. So I have confidence that this is going to be a really fast metric to calculate. Because compared to a Euclidean-based machine learning algorithm, where you have to at least calculate some square roots or at least a square, if we decided to do some chip design here, you'd be able to come up with something that would do this really, really quickly. And you've even got nice ways of sort of breaking it down. You could split it into 4-bit words and see how many of them are zeros, and then add things up in some way like that. Okay, so as I said, the only one I've managed to do completely and I'm confident about, and even then there's some interesting mysteries, is linear regression. So here's the nature of the problem we're trying to do. We want to minimize some error function. And this is a linear function in one variable, so I'm minimizing the error given a gradient and a y-intercept, and a line that doesn't go through every single point. How do I minimize this distance metric? So if this is ordinary least squares, then this is a squared distance kind of calculation. And the way that we solve this is we just take the derivative and set it to 0 and find the solutions for it. And so if you're using a Euclidean metric, so here's my line that I'm wanting to find, my set of data points, and I'm trying to find a line through it. Now, if you look at it, there's quite a few points here that where, y equals x plus 1 is true, but there's also quite a lot of other points that are off that line. So anyway, you minimize the sum of squareds, distances, and I've plotted on the right here for a whole bunch of different gradients and a whole bunch of different y-intercepts, what is the actual sum of squares residual. And you get this sort of, you can't really see the whole thing here, but you get a kind of like convex shape in 2 dimensions in the gradient and the y-intercept. And so somewhere in there, and I've highlighted over here, there is the minimum, the value that minimizes this. And it's really easy. We can analytically find it because we can take a derivative and we can set it to 0 and we can solve that equation. And those of you that stayed awake in whatever the introductory statistics class is at Macquarie, you might remember there was a formula for doing so. And okay, from here on, we're now starting to talk about my research stuff. The only problem with doing this p-adically is that there's actually an infinite number of solutions to that differential equation. And the reason is something like this. If I'm looking at what's the distance here, and let's say I've got my prime number p. If I were to come up with a slightly different y-intercept, so that b variable there, if I added, let's say that I'm very close and some of my points are only p squared away from being exactly on the line, then if I made my y-intercept b plus p squared, or b plus 2p squared, or b plus 3p squared, this bit of stuff on the top here would still be divisible by p squared. But if I were to add p squared plus 1 or p squared minus 1, this thing wouldn't be it wouldn't be divisible by p squared anymore, because it would be p squared plus 1, so it would be congruent to 1 modulo p squared. So there'd be a problem here, which means that as I'm increasing b, for example, there will be many different points at which suddenly the sum of p-adic distance metric suddenly drops down and gets small, and then it gets big again, and then it suddenly drops down and gets small and then picks up and gets big again. There are lots of local minima. In fact, here it is with that same equation with a Piatic metric. I've plotted over here all the local minima that I could easily find. So if you sort of imagine this, it's like, you know, that bubble wrap packaging material? It's like that. You've got lots and lots and lots and lots of local minima all over the place. So problem number 1 is I can't analytically go and find what's the least squares distance, or in my case, because I'm doing this p-adically, I can't find what's the p-adic distance minimum point analytically. Maybe there's some advanced maths that I haven't learnt yet that could do that, but I can't see how to do it yet. And then I have the other problem that the fallback we use in just about every machine learning problem is we say, oh, well, we'll just use gradient descent. We'll just slide down towards lower values. Well, the problem is, depending on where you start, you might end up at the local minima, which might be over here, or it might be over here. It just depends, luck of the draw, of where you started, what minimum you end up in. So that's a problem. And there's certainly some structure here. If you look over at this is what the actual residual distance is, you can see some sort of repeating patterns happening there, with a repeat of every 5 kind of thing, and then there's a repeat of every 25 and so on. And then if you look at two-adically, you'll find that we ended up with completely different answers yet again. Oh, I should just pop back onto the 5-adically. You might notice that it's actually got the right answer. That global minima is actually the gradient 1, intercept 1, i.e. y equals x plus 1, which is what we were trying to find. And if you pop back to the Euclidean metric, it was quite substantially off. It didn't get it right. So Piatic metric. Unfortunately, we end up with a completely different set of global minima. In fact, there's two equally good global minimas that both give you the same value. And so if you're sort of staring here, there's one deep purple point up about there, and there's another deep purple point there. We don't even get a unique solution. So when somebody races up to you and says, find me the best line through these points, Piatically, there may be several very best, equally best lines through the point. So what do we do about it? I'm going to skip over the boring hand-wavy mathematics, but you can prove with a bit of fiddling that in a Piatic space, if there is a best possible line, or if there's a set of best possible lines that have the same goodness value, then you're guaranteed that at least one of those will pass through 2 points in the data set. Now, that's not true in a Euclidean space. You could have a whole bunch of points and a line that doesn't touch any of them, but happens to be the best line through them, just because the outliers happen to play out that way. But Piatically, we do. So that means we do have at least gulp, an order n cubed algorithm, n being the number of points, and m being the number of bits in the integers, because these integers might get quite large as well. And the algorithm goes something like this. Let's just take every pair of points and draw a line through them. And then for every other point, we calculate, well, how far away are you from the line? Calculate the Piatic distance, add it up, and then if that's good and better than anything we've seen before, we hang on to it. If it's equal, then we add it to the set. Otherwise, we throw it away and move on to the next pair of points. So it's a bit inefficient. And I've got a couple of thoughts about how we might be able to do better than that, none of which are working at the moment. But anyway, I have vague hopes that we might be able to do better than the n-cubed algorithm. At least it's not exponentially bad. Now, what happens in all the examples I've seen is points either end up exactly on the line or they end up nowhere near the line. And so close doesn't seem to happen much. Maybe that's just because it's improbable that it happens. But the effect is that it's just finding a large number of collinear points, which isn't all that exciting, but hey, it does work. Right. Now changing topics completely. I'm rushing through this far faster than I should have been, but anyway. The reason I care about this is actually a linguistics problem. And the linguistic problem is this. There are a lot of endangered languages out there where we're about to lose them, often in the next generation, because a lot of people who speak it, the younger generation speak whatever is the more important language, often English, sometimes Arabic, sometimes Chinese. A few of the dominant languages are economically so valuable that they squash everything else out. So we end up with these marginalized people that only the old people speak the language. And we probably don't have very much written text about these languages. The only groups that seem to really do very much in way effectively on documenting these languages are the Christian missionaries who are translating the Bible into these target languages. And usually what will happen is there'll be a project, maybe they'll get a few books done, and then they'll run out of money, or they'll fall sick, or the people who are doing the translation have to go and do other things, or die of old age. And so we never really get around to the bit where we create the reference grammar or the language learning aids or the dictionary. So my question is, can we automatically generate a grammar just from examples? Now, this is an enormously large problem, and I'm only tackling a tiny little portion of it. And at the moment, I'm only tackling a tiny little portion of languages where you have some sort of suffixing happening. Now, that means most of the Indo-European languages. So, for example, in English, to get a past tense, you do ed on the end, for example, or Spanish, you have like different verb forms depending on who's speaking, but it generally is change the ending of the word. But it also works in things like Chinese, for example. So how do I go from I walk, 我坐, to I walked, 我坐了? We're still putting things on the end of the words to represent the different tenses or the different aspects of a verb. So can we think about these kinds of grammar rules as linear transformations? Well, you'd think so, yes, because like to get from house to houses, it's take the word and shift it sort of one space to the left and then add an S on the end. Or things along those lines. Sometimes you have like a linear transformation from sheep to sheep, or that's just, you know, the identity function. And sometimes you get things that, yeah, we can't do them as linear transformations, but we can identify that they're irregular. So mouse goes to mice, for example. There's not really any standard rule about that in English. We don't have house goes to heis. But that's okay. Grammar is not always universal. There are irregular verbs. So even if we can identify here are the, in English, 230 something irregular verbs, at least we've got something that we can run with. So it seems these are very linear transformations. So if they're very linear transformations, then we should be able to use machine learning to find a line of best fit through these in order to figure out our grammar rule. So now let me do something utterly appalling. I'm just going to ASCII encode these words and turn them into numbers. And I don't have to do ASCII. I could have done EBCDEC if I was feeling really IBM-ish and vintage, or I could do a Unicode transformation, or even I could come up with my own way of encoding these words into numbers. So the rule I'm doing ASCII is just look up the ASCII character of A, and you see that's 97. Now that's in the sort of second place. So imagine that this is like a 256 bit encoded word or something like that. So 97 times 256, because it's in like the place value, plus 98, which is the ASCII value for B, you get 24930. So if I do that for house and mouse and sheep and fish and ox and car and dog and person and cat, I end up with these plural values. And at this point, we can tell that this is not going to work very well. Might be easier to actually show it on Tableau here. So I've got person and people, and you can see them because they're quite long words. So when you ASCII encode person, which is my X value here, the median singular number is whatever it is, 123 trillion. And if I go and look at, say, house, the median, sorry, the singular number here, it says median, which shouldn't. It's about 448 billion, which is tiny. But because houses has 6 letters in it, therefore it ends up with like 114 trillion as the Y value. And all the other words in my data set, like if I can move my mouse around here, sheep, mice, cat, and so on, they're not actually on the origin, but they're so small in comparison to all these other values that they might as well be at the origin. They're so tiny. And then if I look log scale, you can see all the short words, a 2-letter singular is going to be like obviously very close. And then we just increase, and then look at the plurals being the Y value. All the 4-letter plurals end up in one row, 5 letters, 6 letters, and so on. So this was the attempt that happens if you try to do an ordinary least squares regression, through this. So even though we know that there's a really simple linear regression that matches the grammar rule, ordinary least squares doesn't get it. It doesn't get it right because you've got so many points at the origin and then a whole bunch of points that are just all over the place that you can't get a hold on it. So here I went through a couple of different algorithms for trying to get this grammar rule, which we know is just a linear transformation. So ordinary least squares, of course, ends up with these floating point numbers, which you can't even use them in the result. So if my x is the singular, so what does 0.89 times house mean? I'm going to end up with some number with like decimal points on the end. So I can't even encode them back into ASCII. So it's actually quite useless. The next two surprised me. So there's two very strong, robust regression methods. The tail-sen algorithm is wonderful. What it does is you just take pairs of points, find the gradient between them, and then figure out which line has the median gradient. And so it's robust to noise. You can have outliers in there and it'll still find the underlying signal. And even tail-sen didn't work in this data set, which in itself is quite surprising. Then the Ransack algorithm, that's basically take pairs of points, draw a big thick texture line through them, and count the number of other points that you happen to capture at the same time. And that Ransack algorithm is incredibly robust. It can cope with half the data set being noise, because if at least 51% of the data set happens to live on a line of some kind, then the Ransack algorithm will be able to find it. And yet the Ransack algorithm said, I give up. I can't even tell that there's any connection between the plural version in English and the singular. You notice the coefficient is 0. It's saying, whenever you ask me for a plural, this is the value, which is the plural of every noun in English. So it clearly, hideously failed. So dramatic drum roll, let's have a look at this in action. So I've got my English noun plurals. House goes to houses, mouse goes to mice, sheep goes to sheep. And just to sort of build up to it, I could just take the first 3 and I could ask, what are the suffix transformation rules if I only had 3 examples? And you'll notice that they're 3 terrible examples. They have no consistency between them. And so Piatically, it comes up with a number of different possible lines through that. I haven't yet sort of written some code to make that a little bit easier to make sense of, but it manages to find some lines that at least will produce an integer result. Let's take, say, 6 data points. So this is now, it's also got fish, ox, and car and cars. And again, it's come up with 2 possibilities, and you'll see that there's something very similar happening here. One of those lines has stayed the same. Moving on, what happens if we say 7, still thinking that complicated rule is the trick? Lots of noise, can't figure it out, then bang, suddenly, once you include that 3rd example of the plural is add an S, suddenly, yep, there's only one possible answer here. And even if I now throw on a whole heap of other rubbish, I will still get a viable answer here. Does anyone have a favorite English plural that is so stupid it doesn't deserve to exist or is noise?
Do you have child and children in there?
That sounds like a good one. Child and children. That should be a tuple. And my example is falling apart really quite badly, and
Double plus.
thank you. I'm now at about 40% real data. If I pop back and just give it another example that is normal, say phone and phones, it should then be right. Yeah, it figures it out. So the cutoff point seems to be once there's about 40%. So it can cope with 60% noise. And that's still better than Ransack. So I'm beating Ransack by probably 10% extra capability of responding to noise. I have a sneaking suspicion if I add another really stupid one that it might be able to cope with that as well. Now that I've got the phone and phones, some other ones. No, not quite working for me at the moment, but there's a certain threshold cutoff, and it seems to be substantially better than Ransack, where we're able to cope even in the presence of vast amounts of noise. I'll jump ahead of my slide. So what I've found is it's around 40%. So somewhat better than any other algorithm out there. And then we, of course, can check back and confirm that this is working. So essentially, we infer on our training set to get our test data set. And so we can see these ones are irregular in some way. They don't follow the dominant rule. This is all well and good if there is just one single rule for plurals. What I'm going to need to do is improve on this algorithm in some way so that it can maybe cluster word endings and then do the linear regression in order to find different declensions, different conjugations, and so on. But nonetheless, I've got something that does work. So punchline is, yep, I'm outperforming, after 4 weeks, I'm outperforming every algorithm in sklearn for robust regression. Well, can we do better than this? Not yet, but it's early days, so I'm not too worried by it. One big problem is performance. That n-cubed algorithm, n-cubed is a problem. Since I'm working modulo p, surely there might be some way of doing it. Maybe I could take all the candidate lines and then just look modulo p, then look at all the lines that work from that, then reduce the modulo p squared and like branch and prune my way up through p squared, p cubed, and p to the fourth, etc. Maybe that's going to work. There's also something else going on that I don't really understand that looks terribly promising. So if you remember my example where I had 5-adically and 2-adically, what I see here is that occasionally you get this incredibly regular pattern here. So this is a 3-adic metric on that set of lines. And what I'm seeing is, yes, of course, I get the same repeated pattern every 3 and every 9 and every 27, because of course that's going to happen. But it's absolutely perfectly regular. The local minima are all separated by exactly the same amount. I'm not sure why that's happening, because when you look at, say, a different prime, you get stuff happening all over the place. There's no obvious pattern here on the 13-adic metric here. And then when I start pushing things up, you'll notice that the correct answer, which is the y equals x plus 1, is the global minima across several different Piatic metrics. So maybe if I hit this with a whole bunch of different prime numbers, maybe I might be able to sort of identify what's the global minima based on the fact that it has to be a global minima in several different Piatic metrics. So that might be another way I might be able to solve it. The global minima has to be the intersection of a large number of local minima in different Piatics. And you'll also notice that as we increase the prime p, something else is happening here where more structure seems to be coming out of it. When I start going to really big primes, I have no idea what's going on here, but you can see that there are local minima following lines and patterns and structure for this equation. And so maybe there's some sort of thing that could be done here. Take a really big prime, calculate everything modulo that really large prime, and we'll then see large numbers of local minima. But those local minima have some sort of structure to them. I don't quite know what's going on there, but it sort of seems like there's something that's got some potential. So what do I need to do now? I'd like to get that runtime down to maybe n squared log n instead of n cubed. At least it's an algorithm then if it's actually got an order log n in there somewhere. We're using that sort of branch and pruning. Maybe there's some sort of analytic solution that I'm not seeing. We've got over a century of number theory work being done in this space. So maybe there is some sort of analytic solution that we can use. My corpus of words, I just made them up. I think it would make more sense if I used some clear corpus and then said, let's look at all the singulars and plurals in this absolutely bog standard corpus that is for some other metric or some other data set that refers to it. Then I could be more confident that that 40% was actually really useful. Maybe I should give it a shot on some sort of low resource language. I think that would be interesting just to prove that it does work there. I mentioned that idea of maybe I want to cluster it first. And then the other thing I'm interested in is maybe instead of ordinary least squares, well, distance minimization, what would nearest neighbors regression do? And I think that would be another interesting kind of aspect to it. So that's my research plan and what I'm doing at the moment. And let's take it away with questions.
If I may ask, in your formula for the least squares regression, you had a del norm, del m term somewhere in there. I imagine you need to have an analytic solution to that to be able to even compute that term. What is the derivative, or like how does that behave?
So if we're doing this Euclideanly, then that derivative with respect to m is just going to be like the b and the y are going to become 0. So you end up with x k. So it basically becomes the sum of the x's. Actually, there's a squared term in there, so you end up with like 2x plus some other rubbish. I think it ends up ultimately being x minus the mean value of all the x's is the thing that solves that. And then I just did that with respect to m. With respect to b, you end up with the same kind of behavior happening. That's if we're in Euclidean space. If we're doing this p-adically, no idea. Presumably the derivative is going to come out with the same to be honest, I don't know. I don't even know how to take that derivative.
What are you computing then when you're taking those solutions?
So how I did it is I did some maths to figure out that I know that the best line must go through 2 points. So just try every combination, which is why it's order n cubed.
Oh, right. So what you have graphed out there is the actual values, not the derivatives.
Yeah, that's the actual value, and then that's the computed derivative just by looking at the local neighborhood.
Got it. Thank you.
Yeah.
I'm going to be a little sort of
Harsh?
maybe just make some critical comments here. So I guess I think there's a couple of things. So first of all, there's a huge amount of literature on morphology induction. So if you look at, there's even conferences and workshops on it. So if you look at things like sigmorphon, you'll actually find lots of papers, lots of data sets, people, that you can compare to.
Yep.
There's also even people that are actually interested in the application that you're working on, which is, coming up with algorithms for inducing grammars for endangered languages. So, absolutely, take a look at all of that stuff.
That's
I
good,
guess also
because Diego was sort of concerned that there wouldn't be places to publish, but
well, so that's a different question, right? Because I'm, when I look at this, I sort of go, I'm not quite sure what the intuition here is. So normally, I think there ought to be some intuition that there is that the representation makes sense, right? And by this, what I mean is, you've chosen to encode the input string as an integer, and you've actually even chosen a particular encoding that puts greatest emphasis on the beginning of the string, right? I mean, so we're basically sort of thinking of this whole thing as being a integer that's represented, base, I guess in this case, 256, right? And so then I think there's a question, does that really make sense, right? I mean, is that a reasonable representation of the problem? Amongst other things, you could, instead of sort of regarding these strings as integers from left to right, you could regard them as integers from right to left.
Yes.
At the very least, then, I mean, given that the morphology in English, at least, is largely associated, inflectional morphology is largely related to the end of the word. At least this would mean that viewed as numbers, the end of the word.
Yes, it becomes more significant.
It's the large, exactly, is more salient than the beginning of the word, which, I mean, in a sense, it's no surprise that if you are working with something like this particular representation, that you need to do something that somehow does not sort of look at the absolute magnitudes. And this Piatic metric of yours certainly does that, right? And in fact, actually, I would guess, I was sort of guessing, actually, if you could pick something which was close to 256 as your P, then in fact, you'll largely, try and forget everything except the last letter, right? I mean, or the last two letters, that's a very good predictor as to whether or not you're going to, essentially, at least in English, if you're trying to figure out whether or not you actually add S or add ES to form a plural, the rule basically looks at the last letter. So if the last letter is voiced, then I think you need to. But there's a rule about essentially when we do schwa insertion in English. So
I think where you're headed with this is, I of course have sort of set myself up with an easy target, because when we do this, like big endian encoding versus low endian, sort of least endian encoding, then Piatics will do better than every other method, because the Piatics are going to care about the last couple of digits there. So yes, what I've done is I've taken an encoding that I know is going to work very well with this metric. And so I'm sort of setting myself up for success in that regard. What I think is interesting is that it's not like normal morphology techniques where we say, I'm going to make up a rule, and you've got a free universe of any kind of rule that you feel like. Here, what I've done...
Generally not, right? I mean, in fact, actually, the sort of morphology that you're looking at here is what's called concatenated morphology, right? In other words, add an S, add an ES, and stuff like that. And, that is comparatively easy to do. And in fact, actually, there's lots of algorithms for doing it that don't even require the text to be pre-segmented, right? So they just simply take a string, and they also figure out where the appropriate morpheme or word boundaries are. things
Yeah.
like that. So
yeah, which is what you'd need if you're doing, say, a Melanesian grammar, where
yeah,
you're
you're
affixing
trying to
a space
induce
and
grammar.
a word. Yeah.
Yeah.
And I think what's interesting here is that I'm bringing in, here's some number theory. And so there's the potential for other things that we've got this sort of baggage of all this Piatic arsenal that we can throw at it. Where indeed there are better solutions out there that you can do without even doing, as you said, without even doing word breaking. But they're computational rather than mathematical in a sense. Like they don't bring another century worth of other research in that space.
But I don't see what this is designed to. I think it would be good to have some ideas of where you think this might be better than the current state of the art. So, for example, you mentioned the issues with local minima.
Yeah.
And in general, all of the unsupervised induction algorithms, once you actually start to try to induce, multiple suffixes, for example, or multiple morphological processes, they often, those unsupervised learning algorithms often face, lots of local minima. If it turns out that the mathematical formulation doesn't, right, that could be extreme, that might be a reason for sort of pursuing something completely different. Unfortunately, what you've shown is that this P-adic stuff does seem to actually have the same local minima. But anyway, I mean, the high-level message is I think it would be a good idea to try and identify some potential things that whatever approach that you're doing can do better than the current approaches. Try and have some ideas as to what issues they might wind up addressing better.
Well, I can actually, just pointing at this one, imagine this wasn't a natural language processing problem. I just race up to you with this data set of X, Y pairs and say, I'd like to find a line of best fit through this that's robust to, there's a bunch of outliers. And this is doing better than, in terms of accuracy, it is doing better than Tailsen or Ransack or Huber, which are the go-to robust regression techniques in these kinds of solutions. So I generated this problem from NLP, but if I race up to you with those numbers outside of NLP and say, what's my line of best fit through it, the Piatic solution does do better. It's more robust to noise than anything else. Now, unfortunately, it's exactly as good as just simply looking at the number of points that are contiguous. But again, I have this sort of hope that we might be able to turn it into order n squared log n or something by doing something analytic that wouldn't be available to just looking for collinearity. So there's one. The other one that I think is going to work is I'm very keen on doing word embedding, because I think word embedding into a Piatic space is going to look so different to word embedding into a Euclidean space. We're going to get all sorts of interesting hierarchical and recursive kind of capabilities that don't exist in Euclidean spaces. That's my guess.
Yeah. So another suggestion is there's also, maybe not huge, there's also a substantial amount of work in hyperbolic geometry for machine learning. So if you just do a Google search, hyperbolic geometry, machine learning, you'll pull up a bunch of stuff, including some fairly nicely written blog posts.
Yeah. And the problem that they face is like computing the derivatives in that hyperbolic space is horrific. Whereas
I think their stuff is usually continuous at the very least, whereas it looks as if, despite the fact that I think you mentioned continuity at the very beginning, based on Chris's question, it's not clear that you've got some continuity to work with here, do you?
Yes, it is continuous. It is. And it's very unintuitive in the way that it's continuous. It's, if I want to be very close to something, I add an enormously big number. Say if I'm P-adically, add 2 to the 1 million. That's a very, very small distance away. So I can get arbitrarily close to some value. So I do have continuity, and I have a continuity that's actually quite easy to compute and a derivative that's quite easy to compute. So I think there's again, hope, not guaranteed, that where existing hyperbolic geometries struggle, that this is a place where I think Piatics might actually have a little bit of an edge.
Anyway, I mean, you know, I realize that at any research, you know, project, there's a period of time when you're sort of just looking around to see, I've got this hunch, I don't know exactly what it's good for yet or whatever, but I do recommend that you try and figure out, you know, what things is it likely to be able to do better than the existing methods do.
Yeah.
Right.
So don't know for sure. As I said, we're 4 weeks in, so we'll have to see what happens. But I think this is the kind of sort of questions that jump out at me.
But certainly, you know, I mean, if you wind up talking about hyperbolic geometries for machine learning, then people are going to expect that you know the research literature on hyperbolic geometry.
Yeah. Well, actually, Mark pointed me to that about a year ago.
Yeah. And if you're talking about
which I did dutifully read, by the way, Mark.
Induction of morphology, then people are going to expect that you talk about, you know, you are willing to compare your stuff to existing work on the induction of morphology as well. So,
yeah. Which I've actually started my sort of, in my literature review, I've got a couple of papers that I've been reading through there.
So I was going to make a similar comment to Mark about the extent to which your results so far are an artifact of the representation that you chose. And I know you said you mentioned word Devec, and you said you're interested in looking at it in embedding spaces. So just a little while ago, I put in the chat window a link to a paper on morphology using the standard kind of embedding spaces that people do now. So you would know, and for a lot of people in the reading group who don't necessarily know, word Devec, one of the earlier embedding kind of approaches, got famous because it has consistent kinds of relationships in the embedding space. So the famous example was you have the vector for king and subtract the vector for male, and you add the vector for female, then the closest vector to that, to the result, is queen. And so there are these semantic relationships, but there are also, these are a little less well studied, but people do know about them, relationships between morphological variants in the space as well. And different embeddings have different kinds of relationships. So fast text character ones are maybe a little better for those kind of things. But so the paper that I linked was by Ryan Cotterill, and among others, he does lots of nice computational linguistic work and cares about morphology and stuff. So you definitely want to relate what you're doing to the kinds of, I mean, that's really a standard kind of representation that they're using there, and they're interested in exactly this question of morphological relationships in that space. In the particular paper that I linked to, they are doing that with Czech. So when you were thinking about what kind of language data you might want to work with, Czech is probably the largest morphologically rich data set. So it's particularly, when people are looking at morphology and problems that you have with morphology, Czech is a really standard one that they look at, just because there has been a lot of work putting together the data set, and it is a complex kind of domain. So that would be a good kind of, this piece of work's, I think, useful to look at for those two reasons.
Yeah. Is Czech actually worse than Russian?
No, it's similar, but it's just that Charles University in Prague, the research put a lot of time into building resources, and they've been doing it over decades.
Yeah. Thinking in terms of these low resource languages, like I'm not talking low resource as in Czech, I'm talking low resource as in like Quayo, with probably about 50,000 words of written language. So it would be interesting to see if we can create embeddings on such a little amount of data And
the thing with something like check, I mean, you can just take a subset of the data and say, what if I only have this?
Yeah.
So, but you know, you have gold standard answers for
what is the correct
questions you're going to pose.
Yeah.
So that's why people typically work with something like check.
Yep.
Yeah, actually, I mean, also one interesting thing with languages like Czech and Turkish and stuff like that is where they actually have morphology happening throughout the whole of the word.
Yeah.
And so what I'm a bit afraid of here is that with your particular metric,
it's going to fall apart. Like,
well,
there's a reason I didn't do Hebrew.
yeah. I mean, you know, you're sort of looking at something which is focused on the end of the word. So the sort of criteria that people often want is translational invariance, right? You know, so in other words, the same sorts of, particularly if you're thinking about processing not just each individual word in isolation, but you're also processing, entire sentences or something else like that. You want to process each word within the sentence in the same way, and so you don't want to have something which is, you know, it works, it does something with the very last character in the sentence, and it does something completely different with the characters in the middle.
Yeah. I mean, things like if I was going nominative to accusative in, say, Latin or German, and then trying to put that into a Melanesian grammar, of course, that's the predicate is a predicate marker precedes the predicate, whereas, of course, in Latin and Greek or German, you're modifying the ending of the word. So, yes, there is a challenge there that I'm not even vaguely tackling at the moment.
Yeah. Well, I think I mentioned Turkish, right? So Turkish has vowel harmony that occurs throughout the whole of the word.
Yeah.
Right? So, but I completely agree with Mark. I mean, I think looking at these these other representations is probably a good idea.
And I think the thing that's interesting here is that it's a really naive and obvious representation, and yet it happens to work anyway. It's kind of interesting that with no real thought applied on my part, suddenly I got terribly good results.
Well, no, you didn't really.
Well,
it's learning to apply, yes, right? I mean,
yeah.
You know, that's.
I have a concern looking at the shape of the metric that linearity is going to get very degenerate for anything other than just adding letters to the end of the word.
Yeah. Yeah. Or adding multiple letters on the end, it'll be fine. But the question was, can we do this as a linear transformation?
Yeah, and it feels like linearity, as soon as you have anything other than a power of 256 in your case, it's going to start really...
It's not going to make sense. Yeah.
It's going to really screw with the entire rest of the word, I would assume.
Correct. Yes, it would.
And is there any way that a linear transform can even learn something like if the word ends in, you know, in a voiced consonant, then add ES, otherwise add S?
No, but if we clustered it first and then used the cluster feature, but if we cluster p-adically, yes, we'll find that immediately.
But, you know, in a sense, then that's the key challenge, right? And as I said, that sort of has proven to be somewhat more difficult, right?
Okay.
That's the sort of challenge that people are sort of looking at is, okay, how do we work out what the appropriate contexts are for different phonological processes?
Yeah, yeah. But I can see the clustering that I haven't done, but, you know, we'll do next. I can see how it would work for, say, Latin or Spanish or any of these other declining, like where the verb, where the vowel sort of 2 steps back.
Well, that's
things.
also the other thing is that usually what happens is these contexts are based on something like syllable representation.
Yeah.
Right. And so it is something like look back at the last vowel. Right?
What you said is very interesting there.
And so you may have to go back some arbitrary number of consonants
to find it.
Yeah.
Yeah, that's interesting. Like the idea of encode each syllable as a different number, modulo some large P, means that you're working that's an interesting thought.
So there are lots of people working on. There's actually sort of a big one of the topics in this literature is, should you be working with syllable-based representations or should you be working with segment-based representations? Right. And the issue then is, if you should be working with syllable-based representations, first of all, where do the syllables come from? In other words, how do you find out what the right syllables are? And then secondly, there's often some sparsity there because there's many more syllables than there are segments, right? So, but I mean, lots of people, including me, have worked on precisely that. So,
yeah.
I was going to mention as well, just to get an idea about, so if you are planning to extend beyond English, and most people who work on morphology do, because English is
so boring.
So I put a link in the chat for a universal dependency tree bank. So it's not exactly what you want, but I was trying to think of a resource where it gives you an idea about the quantity, sort of relative quantities of data available for each language. And there is actually in the tree banks information about morphology in there. So that will kind of give you, an idea of which languages have lots of data and which ones have a small amount of data, and you could use those in your experimental work, possibly with a bit of preprocessing.
So I think what I want to shoot for is actually even lower resource languages than some of the, like, down the bottom of the up and coming. I mean, Somali is not exactly a major world language, and neither is Bengali, but those are millions of speakers. I'm interested in, how can we go on thousands of speakers, because that's where you need to be learning super, super quickly off very few examples. So I will look at that. But
do have Old Church Slavonic, which is currently 0 speakers. So.
That's true. That's true. Yes, but there were quite a few speakers at one point. Yes. Yeah, I'll have a look at that as well, and see how I go on it. So I think it really depends on what I shoot for next.
I would, and I'm speaking as an amateur here as well, I'd advise against optimizing the algorithm on this metric. It feels like it's going to collapse into a version of a discrete problem. If a different metric that is in some way slightly less little endian, or a different kind of regression might work more nicely, but the overall shape of this feels a lot like it's just applying a rule about suffixes, and that's sort of hidden in the shape of what's a linear regression on the Piatic metric. And that specific combination of things. If you tweak something, you might end up with something that's less like a discrete rule, but I think this might accidentally do a fairly discrete computation underneath the hood.
Yes. Yeah. I mean, I think you're right. I think we'll see it'll hit some limits, but I think the interesting question is, where are those limits and how far do we get? Because even if it's only as good, at least we have a sort of a mathematical basis for it, rather than a sort of string processing kind of basis behind it. So.
All right, I think there are no more questions then. So thank you for the talk. There was a lot of discussion here, so it's quite unique. So that's there are no plans for next week. I'm not sure if Mark has any plans for the MLRG, so we can talk about it.
If anybody would like to volunteer, that would be much appreciated. I do have an idea, but I have to talk one of my students into it. That's it.
All right. So thank you all, and I just recording hopefully, so this will be available for later. So thank you all, and bye.
So.
Thanks.
Thanks.